back to recording. I wasn't recording there. So I hope everybody's doing well. Just a couple of reminders I'll include up here. In terms of work that needs, work that's due over the next week or so, I forgot to change this. Modeling homework was due yesterday. Interim report is due on April 6th, and that will also include a peer evaluation. Both of those are posted on LonCappa. Participation question will open on Friday, and that'll be open through Sunday. And then lastly, I have opened up the homework on gravity settlers and centrifugal separators and ESPs, electrostatic precipitators, and that will be due next Wednesday. I moved it to Wednesday so that it didn't coincide with the interim report. So on to a particulate removal, centrifugal separators. So we talked about gravity settling the other day on Monday, and now we're going to move on to a second process, centrifugal separators. This is actually one of the most widely used particulate collection devices. It has been in use for decades, and despite the fact that it is essentially a relatively old technology, it is still widely used. It is a simple, relatively inexpensive, low capital cost. It's useful because it has essentially no mechanical parts and can operate at a wide variety of temperatures. We'll talk about this later with some of the other processes, but that's not necessarily always the case. And some processes do have significant temperature limitations. However, these and also gravity settlers are essentially operational at a wide variety of temperatures. They can also be constructed to withstand harsh operating conditions. And this will again be a limitation with some of the other technologies that we will talk about. These can handle both dry materials, they can handle liquid mists, and ideally they have a small footprint. On your right are two images just to give you a sense of scale. These can be relatively small, fit into a workshop workspace. They can be multi-stories high, as you can see in the lower figure image. So wide variety of sizes and a wide variety of applications. One of the major disadvantages are they typically have relatively low efficiencies, especially for small particles. And that means that they're generally inadequate alone to meet strict regulatory requirements in terms of particulate removal. So generally they're used as pre-cleaning devices for particulate removal. So prior to, we'll talk about baghouse filters later, we'll talk about, as I mentioned, electrostatic precipitators. They may be used as a pre-cleaning device before those. They also can be used for recovery and reuse. You saw that in the video on Monday where they were being used for recovery of aluminum particles from milling operations from a automotive manufacturing parts manufacturing facility. They're also used in the petroleum industry, for instance, to recover certain types of catalysts. They're even used in the food industry to recover freeze-dried coffee. So used extensively. So the way these typically operate is you have air coming in, and it comes comes in through, you can see it here, through an air intake. Notice this is curved, it is tangential. So what it's doing is it causes the air to circulate in a spherical motion. So that air moves in the spherical motion. As it moves, the particles are not able to move with the air. They actually deviate from the air path and contact the walls, at which case they fall down along the sides and then are collected in some sort of a hopper. You can see, if we go back to this figure here, you can see the hopper in the bottom diagram here. You can see that quite well. So this gas is forced into this downward spiral. The inertia, as I mentioned, causes the particles to deviate from the flow paths and hit the wall, and then they fall down. They're typically at this point here. So at this point here, there's some sort of a spring-loaded flapper valve, or a rotary valve. So the dust particles fall, or the material to be recycled falls down into this hopper, and then this clean air reverses direction and moves up out the top. So this is referred to as an involute cyclone separator. There's also a vane axial cyclone separator, and you can see you have these vanes. Again, you've got air coming in. What's going to happen is it's going to move. These vanes cause it to move in a cylindrical pattern, and it's going to move down through, eventually up and out. So the clean air moves out the top. The particles, or the recycled material, flows out the bottom, and then it can be collected. So these diagrams here in table just give you a sense of the cyclone collection efficiency. You can see how, as particle size increases, the efficiency also increases. So as particle size increases, so does the efficiency. And we talk about conventional cyclones, high efficiency cyclones. You can see this here. So you can see with a high efficiency cyclone here, we get much better removal than we would with a conventional. Okay. And we can also have high throughput or high volume cyclones, in which case we get lower removal efficiencies as compared to a conventional or a high efficiency. So the efficiency varies both with particle size. It also varies with cyclone design. Some of the newer models can actually achieve greater equal to 90% efficiency for particles greater than 10 microns. So you can see you're here, okay? For this high volume, we'd only expect about maybe 43% efficiency. Here, maybe 62%. For this one, a little over 80%. However, like as I mentioned, some of these newer models can actually achieve significant removal. One of the challenges, and I'm going to go back, actually go back to this one here. As I mentioned, at the bottom, you've got this spring-loaded valve here. You also have to have a valve at the top. And if air leaks through these, then you can re-entrain material. So these need to be well sealed in order to ensure that the operational efficiency is maintained at what is required. The problem is as we increase in efficiency, so as we increase efficiency, we increase the pressure loss across the cyclone, which increases operating costs. So there's a trade-off between efficiency of removal and the cost of operating these. We can look at a number of other parameters and how they affect efficiencies. And so as each parameter increases, we expect, so as the size increases, we just mentioned, we expect to have an increase in efficiency. As density increases, we also expect to see an increase in efficiency. As dust loading also increases, so the concentration of dust in your inlet stream increases, you also typically see an increase in efficiency. And I'm just going to put this asterisk. This is to a point. So it's not infinite. You can have a extremely, extremely dirty gas and still expect to have increased efficiency. Now, in terms of the cyclone properties, if we increase the body diameter, we expect to see a decrease. So each of these, we're looking at the parameter. As we increase the body length to the diameter, there we would expect to see an increase. So as we increase the smoothness of the walls, we also see an increase. The smooth walls, those particles are going to slide down the walls into the hoppers. They're less likely to get re-entrained into your gas stream. If we increase the inner duct area, then we see a decrease in efficiency. If we increase the exit pipe diameter, we see an increase. Temperature plays a major role, mainly in terms of the viscosity and the density of the gas. So, and as we increase viscosity, we'll see a decrease in efficiency. And as we increase the density, we'll also see an increase in the efficiency. And then kind of combined is both the properties of our gas stream and the properties of the cyclone. If we increase the inlet gas velocity, we typically see a decrease, but again, that is just to a point. One of the things I want to look at is just to compare this in terms of gravity settlers. Gravitational force is equal to mass times gravitational acceleration. Centrifugal force is equal to mass times the velocity of the gas divided by the radius at which it's circulating. So if we take a look at a particle in a gas stream, and the gas has a velocity of 18 meters per second, and cyclone has a radius of 0.3 meters. So if I take the ratio of the centrifugal force to my gravitational force, that's equal to mv squared over r divided by mg. M cancels, and that gives me v squared over r divided by g. So that's 18 meters per second squared divided by 0.3 meters. And if I divide that by gravitational acceleration, that is equal to 110. So basically what that's telling you is the centrifugal force for this situation on this particle is about 100 times greater than the gravitational force. So what that's telling you is that centrifugal separators will be much more efficient than will a gravitational gravitational settler. And that's exactly what we see. And that's one of the reasons why they are used so extensively, because they're much smaller footprint, they're much more efficient than a gravity settler. We can describe the efficiency of a centrifugal separator by the equation that's given here. So N sub E is equal to the number of turns that the gas takes in the cyclone separator. V sub I is equal to the gas flow rate divided by the height. So the height and width at the inlet. So those are both the height and width of the inlet. D sub P is equal to the diameter of the particle, density of the particle, rho, and rho g is the density of the gas. I mentioned W is the width of the intake, and then mu is the dynamic viscosity. And you can see the terms defined here. I've used the notation from the FE handbook. It's a little bit different than in this diagram right here. So that was a mixed flow, a plug flow reactor. We also can write an equation for a mixed flow reactor. Both of these are derived from the equation for the gas residence time, Stokes' law. So in all cases, we're looking at spherical particles. Laminar flow. And no interactions between the particles that would result in agglomeration and increased particle size. So let's look at an example. So we have a situation here where we have a cyclone separator. It's going to operate at ambient conditions, so room temperature. It has an inlet width of 0.15 meters, a horizontal gas velocity of 20 meters per second. Number of turns is 5, and that's pretty common for most commercial or industrial cyclone separators. And what you're asked to do is to compute the efficiency for collecting particles of a variety of sizes, and you're given the density of these particles. So let's just add a slide in here. And so we can let's just write down the conditions that we have. So we have an inlet width of 0.15 meters. We have a velocity equal to 20 meters per second. N sub E equals 5. We have a dynamic viscosity of 1.86 times 10 to the minus 5 kilograms per meter second, and a density of the gas equal to 1.18 kilograms per meter cubed, and a density of the particles of 2.0 grams per centimeter cubed, which equals 2,000 kilograms per meter cubed. Okay. So these are the various conditions we have. We have an equation for the efficiency of removal by plug flow of pi n sub E v sub I dp squared, density of the particle minus density of the gas. And sometimes you'll see that because the density of gas is typically so much smaller than the density of the particle, you'll sometimes see where that's just assumed to be 0. Divided by 9 times WU. Okay, and if we substitute, so let's look first at a 1 micron sized particle, and that is equal to 1 times 10 to the minus 6 meters. So we have I times 5 times our velocity times the diameter of the particle squared. Make sure you remember to convert that to meters, times 2000 minus 1.18 kilograms per meter cubed, divided by 9 times 0.15 meters times 1.86 times 10 to the minus 5 kilograms per meter second. And for 1 meter, this efficiency is 0.025 or 2.5%. So what we can expect to achieve with removal here is 2.5% of these 1 micron particles. And you can see we're not going to get very good removal. So for 1 micron, let's put 5 micron, 6.25 microns, and 10 micron size particles. So efficiency plug flow is 0.025, 0.625, so 62.5% removal for 5 microns. So you can see we get much better removal. For 6.5, we calculate 97.7% removal. And for 10, we calculate 2.5, which means we get 100% removal. For mixed flow, we just take the fractional value that we previously used, and the equation that we're going to use for that, that is equal to 1 minus exponent of minus the plug flow efficiency. And this will give us 0.0247. So you're going to see less removal because you're assuming that you have some mixing. Here, 0.465, and it gets, you see that as the removals increase, you actually see a greater difference. So 46.5% removal. And about 92% removal there. One of the things to remember here, and the way that these are coded, if you get an answer that is greater than 1, so greater than 100%, Ln kappa is coded that the answer is 100. Okay, so it's coded with an if-then statement. So remember that if you do get an answer greater than 1 for your removals, the answer is 100%. You can't get more than 100% removal. Any questions? As I mentioned before, these cyclone separators have been used for decades. Back in 1951, an engineer by the name of Lappel published a semi-empirical relationship to calculate the 50% removal, or the diameter of a particle that would result in 50% removal of that size particle. And that is referred to as the cut diameter. So this is the equation for the cut diameter, very similar to the previous equation. All of the parameters have been previously defined, And this is widely used in the industry to estimate removal efficiencies and to design cyclone separators. In 1980, Theodore and DiPolo developed this equation here, and this is from the FA reference handbook. This is an equation that allows one to take that cut diameter and use that to predict the efficiency of any size particle. So it's using the relationship or the ratio of the cut diameter to the particle diameter, as you can see here. So I've given you, again, this the material from the FE reference handbook. You see here you have that cut diameter equation. You have all the parameters defined. And you have a diagram that defines all of these terms. Note here, if this is a log-log plot, so if you're using this, be careful to make sure that you do recognize that it is a log-log plot. So you're looking at here the ratio of the diameter of your particle to that cut diameter. It's actually the inverse of what's in this equation. So just be careful with that. Another equation that is typically used is what's given here. This is an equation to calculate the number of turns. So as we talked about, the air comes in, it's going to make number of turns, and then it'll go out the top. So in order that these number of turns is dependent on the length of the body cyclone, the length of the cone. So you can see here, this is the length of the cyclone, the length of the cone, and 1 over h. Okay, so actually the air comes in here. Typical values for number of turns, as I mentioned before, is about 5. Now, this table here again is from the FE reference handbook. You can find similar tables in a number of textbooks. Basically, these are dimensions for classical cyclones. And you can see you've got high efficiency, conventional, and throughput. These actually can be used as ratios. What isn't included in here is the body diameter. So the body diameter, this D, this is D over D. So that is assumed to be 1. So basically you can use this. If we assume this is 1, then for instance, we would have an inlet height of h. If our body diameter was actually 2, then you would multiply your height by 2. So basically you can see, you can use these values as ratios to D. Okay. So again, if you double D, so D is 2, these values would double. That's not stated in the FE reference handbook. So make sure you realize that in case you do have a problem like this on the FE. So let's look at an example. So we have a conventional cyclone, has a body diameter of 1 meter. A airflow rate is 150 cubic meters per minute at a temperature of 350 Kelvin and 1 atmosphere. Air contains particles with a density of 1,600 kilograms per cubic meter and the size distribution that's given below. and you're asked to calculate the overall efficiency. Let's just add a slide in here so that we have some space. Now, we need to get some parameters for the cyclone. We would get them from here. We have a conventional cyclone, so we're going to use these ratios right here. Okay, and we've said we have a body diameter of 1. So our inlet height is equal to 0.5 meters. And this is straight. This is from slide 17. Okay, so from the table on slide 17, my inlet width would be 2.5 meters. My body length would be 1.75 meters. My cone length is 2.0 meters. The diameter of the gas exit piping is 0.5 meters. The diameter of my dust outlet is 0.4 meters. Okay. We said that our flow rate is 150 cubic meters per minute. Temperature is equal to 350 Kelvin. And the density of my particles is equal to 1,600 kilograms per cubic meter. And density of the air is about 1.1 kilogram per cubic meter at that temperature. And the only other thing we didn't include was the body diameter, and that is 1.0 meters. Okay. So we have both parameters. The cyclone dimensions are from this table here, and the other parameters are either given or you would have to look them up to determine your density, and if you needed it, the viscosity. So Q over HW is equal to my inlet velocity, and that is equal to 150 cubic meters per minute divided by 0.5 meters times 0.25 meters, and that is equal to 1,200 meters, meters per minute. N sub E is equal to 1 over H LB plus LC over 2. So the length of the body plus the length of the cone over 2. And that is equal to 1 over 0.5. It's 1.75 plus 2.0 over 2. And that is equal to 5.5. The diameter, or cut diameter, is equal to 9 UW over 2 pi N sub E, V sub I, density of my particle minus density of gas, all to the 0.5. And that is equal to 9 times 1.8 times 10 to the minus 5 kilograms per meter cubed times 0.25 meters over 2 pi times 5.5 times 1200 meters per minute. I need to convert to seconds times 1600 minus 1.1 kilogram per meter cubed. And that is equal to 6.15 times 10 to the minus 6 meters, or 6.15 microns. So it's about 6.2 microns would be my cut diameter. Now, what you're asked to do is then calculate the total efficiency for this gas stream. So the first thing I need to do, I've got it here, is I need to calculate, this is my average diameter. So it's just an arithmetic average. So for instance, this is just 0 plus 2 over 2, that equals 1. 2 plus 4 over 2 equals 3. So I'm just calculating the average diameter. I'm then going to calculate the ratio of d of our cut diameter divided by the average diameter for that size particles. So our cut diameter was 6.5 microns. I'm dividing by 1 micron. Okay, here, I'm going to take 6.15, and I'm going to divide by 3 to get this ratio. And I'll just do that for each of the particle sizes. The next thing I want to do is calculate the efficiency of collection for any particular size particles, and n sub j, and j is just that particular particle size. That is equal to 1 plus, and this is the same equation that we had before, dpc over dpj average squared. And so for instance, if I, for the 1 micron size particle, this is just 1 over 1 plus 6.15 squared, and that is equal to 0.03. So that's this value right there. It's just an Excel spreadsheet. And the mass collected here is just equal to this mass percent times the efficiency for that size. So this is just equal to this 0.03 times 1. This is equal to, and this is in percent, this is equal to 0.19 times 9.0. That gives me a value in percent. This 9.0 is percent. So this is all percent values. What I'll then do is sum this, and this would be the total removal, about 69% removal we can expect for this mixture of particles in this air stream. Now, suppose we want to remove these smaller particles and we want to get better removal. What are the options? The options are either to make the inlet width smaller, but if we make that inlet width smaller, we can we limit the amount of, or the flow rate of gas that we can treat, or we can increase, and change this to, I changed the notation to be consistent with FE. So we can change, we can increase this velocity. If we increase the velocity, what happens there is we increase our efficiency, but we're going to increase here. So we increase efficiency, but we increase the head loss, which means that that's going to increase our operating costs. So one of the options that we can accomplish there is what they do is they actually take smaller cyclones, essentially combine them together, creating metal turning valves to add. So the dirty gas comes in here, then moves through these multiple cyclones, and then the clean gas out the top, and our dust or particulates fall out the bottom, just as before. So basically these multi-cyclones are numerous cyclones housed together in one unit, so that we can make smaller inlet widths, but we can still treat high volumes of flow. The last thing I want to look at is pressure drop. I'll introduce the equations. I think what we'll do is we'll do the example first thing on Friday. But I want you to have some sense of these pressure drops. So our pressure drop is related to what is often referred to as a velocity head, and also what is referred to as this is a pressure drop expressed in the number of inlet velocity heads. Okay. And typically this K value ranges in about 10 to 12. Your HV value, all sudden expansion. So if you have a sudden expansion, HV is equal to 1. Sudden contractions would have an HV value of 0.5. Typically for most cyclones, this is around 8. Typically that's what we would expect. We can also calculate the power consumed with this equation here, and this is just our flow rate times the change in pressure. So in order to produce this cyclonic flow, what we need is we need either a fan or a blower to overcome this pressure drop. So we've either got to push air through, or we've got or we're going to create a suction. So we really have two different ways to operate this, with either a blower before or after. If we put this blower before, the problem is we're treating a dirty gas. So what the problem there is these particles then can get into the bearings. So they're going to cause wear on the bearings. They can collect on the blades. And that results in the fan being out of balance. and requiring mechanical maintenance on them. Or we can have it after. The problem with after is we're creating suction or a vacuum on the system. And then I showed you before where you have that seal at the bottoms. If we have a poor seal at the solids removal, we end up with gas being sucked in to the cyclone, and we end up with entrainment of particles of air, but it entrains the particles back into the gas stream, and we end up with pore removal. So we'll end there for today, and I've got this example here. We'll quickly do this example on Friday, and we will also look at electrostatic precipitators. So we'll end there. I will be online for office hours, so if you have any questions, just feel free to stop by, and happy to answer. So thank you.